So hi everybody, this is Miss Doherty for the first part of your matter lecture outline for the unit on matter. And today what our focus is going to be are the changes that matter can undergo, whether physical or chemical, and how matter can be described by its physical and chemical properties. So let's start first with what is a definition of matter, or what is not matter. Now if you take a look at this beautiful reef scene, it's fairly evident that the fish and the coral and the water that they're swimming in is definitely matter. But that bright light you see in the upper right corner is not matter because it's clearly sunlight or energy from the sun. So what we need is a way to define matter. And when you look at something, say like a fire burning, anything that's giving off heat or light is definitely something that's on fire, and that's definitely not matter. And that leads us to the eternal question in the upper right there, does love matter? Now we need a definition of what the properties of matter are. So let's give it an official definition. Chemistry is the study of matter and the changes it can undergo when energy works upon it. And matter is anything that has mass and takes up space. That is, it has a volume where it occupies space. Any kind of matter that is uniform and unchanging in its composition is called a substance. Now you can also call this a pure substance. That would include things like table salt and water. So down below you can see pictures of a salt shaker of salt, the compound sodium chloride, and you can see a drop of liquid water. Water is pure when it is clear, has a boiling point of 100 degrees, has a freezing point of 0 degrees, has a density of 1 gram per cubic centimeter or per milliliter, and those properties are constant for pure water no matter where on the planet that you sample water from. So those are examples of compounds. As you know, water is H2O, made up of 2 elements, and salt is sodium chloride, also made up of 2. Elements, by default, then, are pure substances as well, and you can tell that you have a compound being formed when you have 2 possibly or more completely different elements that combine to create a totally brand new pure substance, such as the salt. Sodium metal is a soft, shiny metal that's highly reactive and explosive in water. Chlorine gas is a green, poisonous gas, and when you let the two react fairly violently, what you get is a stable, white, ionic, solid compound that's relatively safe to eat in small amounts. Again, though, it's a pure substance, salt, because its matter is uniform and has unchanging composition. Seawater that might be taken from different seas or oceans across the planet cannot be described as a pure substance. Seawater is a mixture, and that's because if you have an inland sea, for example, its salinity might be much more concentrated than that, say, in the open ocean. So it will have differing composition depending upon where on the planet that you sampled it from. We'll do more on mixtures later. But matter can definitely be classified by its properties. So let's take a moment and look at a short video about the properties of matter.
Include melting point, boiling point, color, density, magnetism, crystalline shape, malleability, ductility, luster, and refractive index. The physical properties of matter can be observed without any change in the matter's chemical composition. Chemical properties, on the other hand, can be observed only when matter undergoes a chemical change. Here are some examples of chemical properties. Hydrogen peroxide decomposes easily into oxygen gas and water. iron reacts with oxygen to form iron oxide. Sodium metal reacts with water to give off hydrogen gas. Sodium hydrogen carbonate, baking soda, reacts with acid to give off carbon dioxide gas. Lead nitrate reacts with potassium iodide to form a yellow precipitate of lead iodide. Red phosphorus can undergo combustion in air.
Now, if you missed any of those definitions, don't worry. Here's another list. And of course, the beauty of these vodcasts is that you can stop, rewind, play again at any time that you wish. So let's define physical property. A physical property is one that can be observed or measured without changing the composition of the matter. All you have to do is use one of your five senses, not using taste, to observe the matter. Now, clearly, state of matter, whether you're solid, liquid, or gas, is a physical property. Density is defined as the amount of mass per unit volume, typically gram per cubic centimeter or gram per milliliter. Solubility has to do with the ability of a substance to be dissolved in a specific solvent, the thing that is doing the dissolving. Texture is how it feels. The color is fairly self-obvious. The mass is a physical property, as well as odor and taste. Minerals can be rated based upon the hardness scale, and pure substances have very specific melting and boiling points. You saw a few others in the video I'd like to explain a little bit. The refractive index is a way to measure how much a crystalline substance could bend light. Also, the narrator described malleability and ductility. Malleability is a property of metals in which you can pound them quite thin and flat into a thin sheet. Excuse me. And ductility is when you can stretch wire, a piece of metal, into a thin wire. And all of those properties have to do with the forces of attraction that substances can have at the submicroscopic level, but again, we'll discuss that more later. So that's a fairly good list of physical properties. Now, the state of matter is also known as the phase of matter, and we're going to be using in chemistry three common phases of matter: solid, liquid, or gas. We will also be discussing aqueous solutions, solutions that are derived by dissolving something in liquid water. Elements and compounds can move from one phase to another phase when a physical force such as heat is applied to it. Now, quick side note, heat and temperature are not the same thing. We can use temperature to measure the amount of heat that is flowing, but the universe is guided by a couple of important laws, and one of those you already know. Hot things cool off. Heat always flows from places that are hot in the universe to places that are cooler. Now, we can measure the amount of heat flowing by changes in temperature, and we'll deal with the definition of temperature later on. But a last quick explanation, I could have two containers, a teacup and a bathtub, that are both at, say, 70 degrees Celsius. They both are at the same temperature, but which one has more heat? Let's think about that. The answer is, of course, the bathtub, because the bathtub has more mass. So please don't get heat and temperature confused. They are separate things. Now let's take a moment and look at a little video of when you can get energy acting upon matter to get it to undergo what we call a phase change. So it takes a second for this to come up here since it's an internet link. What you'll see when the image comes up is on the right-hand side, they will have a picture of what it looks like to see the substance in a microscopic view. Here is the substance that is going to have heat applied to it or taken away. And over on the far left, we can see the three common forms of matter that we're going to be studying. So you have a little bit of a definition to do in your PowerPoints about what makes up a solid, a liquid, and a gas. Let's take a closer look at a solid. As you can see, the particles of a solid are arranged in a tight, regular pattern, and they kind of are moving a little bit, so sort of jiggling, but they're staying in a fairly organized pattern that you can see. And this has to do with the forces that hold matter together, again, a subject of another chapter. But I know I can break those forces down if I add some heat, and now you should see our temperature rising. The solid substance is melted into a liquid as the forces that hold it into a solid, organized form of matter are broken down. So the definition of a liquid is when the particles move easily past one another. That's called fluidity, or the ability to flow. They're still fairly close together, but no longer are they in the nice, neat, even arrangement as the particles were in a solid. And we can add even more heat and watch that temperature rise. To see, you can turn that liquid, complete with sound effects here, into a gas. And now this liquid is boiling. What Superman would see is that there's a lot of space in between the gas particles in the submicroscopic view, and of course they're rapidly bouncing off each other and bouncing off the walls, the most disorganized form of matter. So let's go back to our solid and recap. The substances can be changed from one form or phase of matter into another by the addition or the removal of something like, for example, heat. So let's return to our PowerPoint. Okay, so those are the phases of matter and some of our definitions. Now let's look at one odd form of matter that is a little bit in this classroom. If you look up at the fluorescent lights in our classroom, there might be a little bit of plasma in those, but you're not going to find too much because plasmas are consisting of fairly freely moving particles that are charged, electrons that have a negative charge or ions that could be positive or negative. And the only way you can have that happen is when they're formed at very high temperatures, when electrons get stripped from the neutral atoms. Well, that occurs in places like our sun. So stars, including our own sun, the northern lights that you see, which are caused by particles from the sun interacting with the Earth magnetic field, and ball lightning are examples of a strange sort of form of matter called plasma, not something we'll be experimenting with. And here's a lovely shot of some of that lightning. Now, physical properties can be further subdivided into intensive or extensive properties. And extensive properties are pretty easy to remember if you just remember it has to do with the amount of matter that is present. So if I have more matter, then clearly its mass, its volume, and its length are going to be larger. So extensive properties do depend upon the quantity of matter that is present. Therefore, the opposite would be true. Intensive properties do not depend upon the quantity of matter present. And examples of intensive properties would be things like density, color, texture, or boiling point. Now let's zero in on one or two of those. I could have a teaspoon of sulfur or a gigantic mountain of sulfur from, say, some sulfur refining plant. It doesn't matter if I'm looking at the teaspoon of sulfur or the mountain of sulfur. That color that the sulfur is going to have is yellow. Also, if I was to sample one certain unit volume of that sulfur, let's say a cubic centimeter, whether I got the cubic centimeter from the teaspoon or whether I got the cubic centimeter from the mountain of sulfur, sulfur is going to have a very specific unit mass, density that is, the amount of mass per cubic centimeter. And let's say I let you touch the sulfur, not always so safe, but it would have, in that particular type of form, sort of a gritty, granular texture. All of those things that I just described do not depend upon the amount of sulfur that is present. So therefore, they are intensive properties. Now let's zero in on chemical properties. We've been looking at physical properties. Let's look now at chemical properties. And the key feature about a chemical property is that it's when something undergoes a change, when two or more substances chemically combine, or sometimes decompose, but change into one or more other substances. So if I wanted to describe the chemical property of a base, I would say that the base is reactive with acids. If I want to describe the chemical properties of, say, cellulose or paper made from that, then I would say it has combustibility. It can catch on fire. Iron left out in the air can react with oxygen to create iron oxide, which we know is rust. And I'm not sure personally if I would call radioactivity a chemical change, because as you know, radioactivity has to do with changing the number of subatomic particles, neutrons and protons, that are in the nucleus of atoms. And we're not doing too much of that at all, I hope, in chemistry, because obviously it can be quite dangerous. But in the sense that radioactivity can cause a change into a new element, I guess in that sense you could think of that as a chemical property, but I would stick away from that one. Another way that you can rank or decide whether substances are undergoing physical or chemical changes is to sort of look at the completeness, for lack of a better word, of the change that's being wrought upon the substance. So for example, we've got a tree burning in a forest fire here, and that definitely is much more complete change in the matter in the tree than the simple act of the lumberjack cutting down the tree. Now, reversibility is another property of matter that can be used to try to discern whether the changes that it's undergoing are chemical or physical. It would be quite difficult to reverse, I agree, the cutting down of this tree back into a living tree, but at the very least, it's still showing the same composition, the same shape, the same structure. Sadly, it's now lying horizontally instead of vertically. So more complete change is more likely to be something that's describing a chemical change, and it could also be described as a chemical property. So let's go now and talk about some changes. A physical change you should have some familiarity with. In these bowls that you can see, we have ice cubes melting into liquid ice. And as you can also see, the temperature is higher here, and the ice cubes are turning into liquid water. So when we talk about a physical change, we want to make sure we're describing something that could be changing shape, like the ice cubes are turning into liquid, or changing state. Ice cubes went from a regular cubic pattern into no particular shape. Change of state would be solid into a liquid. You can even have, for example, a physical change, which means that the substance is not altering its composition if you do something like dissolve a solid solute, salt, into a liquid solvent, water. And I know that that's a physical change because if I wanted to try to see if the reaction or the change could be reversed, I could easily drive off the water through evaporation, and if I wanted to, collect that steam through a condensing tube and prove that it is indeed water as it cools off and condenses. And left behind in the container would be the solid solute of salt. So a physical change is a change which can cause the shape or the state to change, but it doesn't change the composition. The liquid water in that bowl on the right is still H2O. It's just not locked into a crystalline structure like the solid water or ice was. Chemical changes, however, definitely change the chemical properties of a substance. And as the name implies, it involves changing your original substance into something completely new. Here are some examples of some chemical changes. Combustion we've talked about, clearly something that's on fire. Fermentation is when a microorganism such as yeast can consume sugars to produce, among other things, alcohol or possibly carbon dioxide. Oxidation is a reaction in which one atom is losing electrons to another. We can see evidence of oxidation when you, as I mentioned before, have a piece of iron out in air being oxidized and having it turn into iron oxide or rust. Corrosion is the, say for example, a substance that's being corroded or eaten away by another substance. And we've already mentioned things can have reaction with an acid or reaction with a base. A good example of a reaction with an acid that is a chemical change is that many metals are reactive with acids and will decompose or will react to produce metallic salts and also hydrogen gas. But the key feature is we have new substances that are forming in a chemical change, And we are going to have to be able to keep our eyes open to what are some evidences of chemical change. Now this one is always a chemical change. The word precipitate does not mean precipitation like in rain, but it does mean that you have two clear solutions. Like this is a solution on the left-hand side of a person here is holding a beaker of either silver nitrate or sodium chloride. It's hard to tell because they're both clear liquids. But when the silver ions from one container bump into the chloride ions in the other container, as you can see here if you look closely, a solid white precipitate of silver chloride is forming. A little bit more colorful on the right-hand side, a little bit more poisonous too, since chromate, which gives the yellow color to this beaker, is also carcinogenic. Let's just take a look though at the formation of barium chromate. There are clear barium ions in this part of the liquid, and there are clear but yellow ions of chromate in this beaker. And if you look at the interface where the two substances meet each other, now they're cloudy, and we've made a solid precipitate, something like you can see here in this test tube. And it's opaque, you can't see through it. If you were to spin it in a centrifuge, the solid would fall to the bottom of the test tube. That absolutely, 100% of the time, when you see the formation of a precipitate, that's absolutely evidence that a chemical change has taken place. Another evidence of chemical change could be color change. Now this one is a little trickier, so let's look at the one in the example here. In the fall, the green chlorophyll that had been present in the leaves of these trees starts to diminish, and that allows the more beautiful orange and yellow and red plant pigments to be able to come to the forefront. So we see the change in the color of leaves, and that is a chemical reaction. However, you're going to want to be careful. As you will see in some upcoming labs, it's possible to have a change in color, but it's relatively reversible. That is evidence of a physical change, not a chemical change. Let me give you one example right now. I might have a candle that's made of solid white wax. If I melt the wax, it becomes liquid wax. It's still wax, but the color has now changed in its liquid form to clear. So I have a color change, which at first you might think is a chemical change, but if you remove heat and let that liquid wax re-solidify back into solid wax, it's back to being white again. So you can't always rely on color change as being a sole indicator of a chemical change or reaction, but it's a pretty good one most of the time, especially if it's coupled with, say, the formation of a precipitate, or if it's coupled with the formation of a gas. As I alluded to before, here is a beaker full of acid into which someone has inserted a strip of metallic zinc. And if you do careful examination right here at the interface of the zinc and the hydrochloric acid, you can see bubbles of hydrogen chloride gas coming off. Not seen to you in this clear liquid is that the hydrogen chloride is being turned into zinc chloride. Gas evolution, or the production of a gas, is definitely evidence of a chemical change in this case. When you see the giving off of heat or light during a reaction, that's also good evidence of chemical change. If you've already done the lab, or as we get ready to do it, or if you saw my demonstrations in the first few days of class, this is something made out of magnesium that's burning safely far out in an open field. A tremendous amount of heat and light is being given off, and that's good evidence of chemical change. And one thing that we need to talk about as we get into the future is that when chemical changes take place, we can neither create nor destroy matter. And I think I'll stop here. It's a good stopping point. So we can look at the quantitative changes in matter and how matter is always what we call conserved. You can neither create nor destroy matter. And that's it for part 1 of the Matter PowerPoint.